morning all. In today's class we are going to see about matrix stiffness method. So far we have seen 4 methods, on total 5 methods. So first one is strain energy method, that is unit 1. Second one is slope deflection method. Next we have seen moment distribution method. Fourth one matrix flexibility method. And finally unit 5, today we are going to see matrix stiffness method. So first we will see the definition of stiffness. So you know that any structure has its nature, like whether it is flexible or stiff. So in the last unit we have seen the flexibility nature of structures, exactly structural elements, and here we are going to see the stiffness. So stiffness is defined as the ratio of force to displacement. That is the amount of force we are applying on structure. So that will cause some displacement or deflection. So exactly the ratio is taken as stiffness. So in this we have to know one more term, that is stiffness coefficient. So this stiffness coefficient is applicable to the pin jointed frame, and you can find it using the formula AE by L. AE is axial rigidity and L is the length of the member. So apart from this, the final one in introduction is the kinematic indeterminacy. So this kinematic indeterminacy is denoted by Ki. We have already seen static indeterminacy SI. Similar to that, this is kinematic indeterminacy. So in static indeterminacy, we are very much reliable on the equilibrium conditions. Then the support, here only the support plays the major role because we deal it with the displacement. The stiffness method is also known as displacement method. So we know the type of supports. First one, fixed. So for the fixed one, the Ki value is 0. Next, for the hinged, the value is 1. For roller, it is 2. So here directly we can use the Ki values for analyzing the structure. So that's all about Ki. So we'll see a simple problem in which we can find out the Ki value. So now let us try to find out the Ki value for a continuous beam which is fixed at A with simple support at B and C. So we can find out the Ki value directly, but conceptually we have to know something that we all have to remember this. So first is fixed, next is with simple supports. So the displacement is possible at B and C. So displacement is possible at B and C. Displacement can be denoted by either this del or this del. So I will keep at B as del 1 and at C as del 2. So one by one we can assume unit displacement, and then we can even find out the rotation matrix as we do it in flexibility method for finding out the transformation matrix. So first Ki. So Ki I told it depends on the supports. So for fixed it is 0. For simple support, that is hinged, we have 1, and C also we have 1. So on total it is 2. So this is how we have to find out the Ki, that is kinematic indeterminacy. Next we will see how to find out the rotation matrix. So this rotation matrix is similar to the transformation matrix that we have seen in the flexibility method. So this rotation matrix is denoted by beta. So we can take the same example also. A continuous beam, A is fixed, B and C are with simple support. So for this, previously we have found the Ki value as 2. Okay, after this, we have to draw the primary structure. So this primary structure, drawing of primary structure is similar to that of the matrix flexibility method. So here we will draw the primary structure. Primary structure is nothing but you have to indicate where the displacement is applied or assumed. Okay, so this is primary structure. It is also denoted by PS. Next, for drawing the orientation diagram, there are two spans given in the continuous beam. So you can split the span and draw the orientation. So we all know that orientation can be taken as clockwise or anti-clockwise. For an ease, you can take it in clockwise. Then start numbering. So now the system coordinate we have to find out. So which is nothing but in how many times you are applying the displacement. So which is 2, and here this element coordinate is based on the orientation diagram. You can take the number as 4. So all these are found in order to find the size of the matrix. So size of rotation matrix. The formula is Ne by Ns. So Ne is 4 and Ns is 2. So now we have to develop a matrix such that the size is 4 by 2. So for that, first you can apply or you can take del 1, which means unit displacement is applied at B and the displacement at C is 0. So under this condition, when the displacement is applied at B, the influence is only there. Then in the rest of the places, it is 0. So which is one 0 transpose. So our next one is the displacement you can apply at C and the displacement at B is taken as 0. That is, unit displacement is applied at C. Draw the orientation diagram. Then based on the displacement assumed, you can just mark whether there is influence or not. If there is influence, you can mark it as 1. If you want to mean that there is no influence, you can indicate by putting 0. So this is 0, 0, 0, 1 transpose. So now the formation of rotation matrix is over. So first you had a row with transpose which is 0, 1, 1, 0, and next is when you apply displacement at C, it is 0, 0, 0. So this is formation of rotation matrix. So the basic things are that you have to remember is the kinematic indeterminacy, drawing of primary structure, orientation diagram, and finally you can develop the rotation matrix. So with these all simple steps, we will be able to analyze continuous beams, rigid plane frames, and pin jointed with slight modification we can analyze with the same method.